Saxon Algebra 2, Lesson 116. You guys, we are going to wrap up the week with a lesson that is a little bit lighter and easier to digest than some of the beasts we've been wrestling with this week. We're going to talk about permutations, which I believe are new this year, and probability that we've been talking about for the past year or two. These are the games of chance. Permutations come pretty natural to most students, and so let's play around with those. The idea here with permutations is, imagine that we have three letters, three tiles, like Scrabble tiles kind of. One has an A, one has a B, one has a C on it, right? And what we're trying to find is how many different combinations could we make of these three tiles, just these three, right? We can't use any others. We can't repeat a letter because we don't have two A's or two B's. We can only use each letter once. So let's go through and just logic it out. I guess you'll be watching me logic it out. What are the different combinations? Well, we could have A, B, C. And then let's leave the A and flip the other two. It could be A, C, B, right? Now, those are the only combinations with A in the first place. But what we could do is we could move B into the first place, and we could do B, A, C. Or we could leave B there, but then flip the other two, B, C, A. Okay, and then we could also move C to the beginning of the line, and then do them alphabetically or reverse. But that's it, right? Those are the different permutations or arrangements. That's what that word means. That we can make with those three tiles. And so the answer would be there are six, I like to use the word ways, 6 ways those tiles can be arranged. Okay, that's cool. That makes sense. But we don't want to have to write them out every time. That's annoying, right? So instead, what we do is we imagine visually what our solutions would look like. We said there's 3 tiles, right? Here I drew them separately. Now I'm drawing them together, all right? So this is the way we do this. We start here most of the time. So there will be an exception to that. And we say, we've got these 3 tiles. How many different of those tiles could we put in this box? We could put the A or the B or the C, right? So that means there are 3 different choices. Once we put a tile there, how many choices do we have for this box? Well, no matter which one we put in, once we put in one of them, we only have 2 more choices for the middle space. And then once we get those 2, we only have 1 more chance, right? 1 more choice for the last one. That's the mental process we use, and then we multiply. 3 times 2 times 1 equals 6, and we get the same answer. Okay, so this is the process that we're going to use to work these problems. That was one of John's cheater problems that wasn't actually a problem. How many different ways can the numbers 3, 5, 7, and 9 be arranged if no repetition is permitted? Okay, that was like me saying these were on Scrabble tiles, so you can't use them over and over. No repetition, and I just write no rep, means we can't use the numbers over again. So once again, we visualize our solutions by drawing a box, and we're arranging the 4 numbers. We have to use all of them, right? Okay, so when I go to fill in this first box, I can put any one of those numbers in. So I have 4 choices. Now that I've put in a number in here, puttin' is not a word. Well, I mean, except for that delicious warm dairy dessert. That's puttin'. But I digress. Now I confused myself. Oh, so we could choose any one of those 4. But once we've chosen one of those, one of these numbers goes away. And so when we go to choose our second number, there's only 3 left to choose from. Once we've put 2 numbers into the first 2 boxes, we only have 2 numbers left. So there's 2 and then 1 to choose from. So then we multiply. And I'm not going to write it out like this because you understand. 4 times 3 is 12, times 2 24 ways. We just multiply the numbers in the box together. Sorry, I'm behind in my smiley faces. Oh, well, this technically wasn't a problem, so that's all right. All right? If you're adverse to drawing pictures, get over it, because this is a really great way to understand these, and they're going to get more complicated. I mean, you know how this works, right? How many four-letter signs can be made from the letters in the word equal? Okay, so that's 5 different letters, isn't it? But we're making 4-letter signs, and we're told repetition is permitted. So in my notes, I write rep okay or no rep. Repetition's okay. Okay, so we're making 4-letter signs. So what I want you to imagine is, have you ever seen, oh, all the moms now have the felt boards, right? The little message boards in your house. Oh my gosh, my book just fell on the floor. And they have the little ribs on. I mean, I have one too. They're felt, and they come with the plastic letters that you can put on there to make a sign, right? And they're all over Pinterest. We're imagining those. They come with not just one of each letter, but like a bunch of each letter, right? So you can repeat. Now, there probably aren't a ton of cues, but let's just pretend that we have a set that has an infinite number of all the letters, which would be really big. But anyway, you understand what I'm saying. So when we go to fill in this first blank, we can use any one of these 5 letters. When we go to fill in the second blank, it's okay if we repeat the first letter, and we have an infinite supply. So that means I have 5 more options for the second one. I can repeat any of the 5 letters there, and I can repeat any of the 5 letters there. Now, some students get freaked out on these problems because they think, but I have 5 letters. It's okay. That's what we're showing with those 5s. We only are going to use 4 letters at a time to make this sign. I'm not sure what the significance of the sign is, if we're just making like meaningless combinations of letters, but whatever. We're not going to worry about that. Your mom's just in a crazy mood, and she's trying to see how many ways, how many permutations of the letters in the word equal she can make. So it's fine. We multiply 5 times 5 times 5 times 5, and I'll tell you right now, it's 625 ways. That's a lot of ways to make garbage words on your cute little trendy whiteboard, blackboard. Some of them are pink now and, you know, other cutesy colors. So anyway, I digress. When it's okay to repeat, our calculations yield much bigger numbers. Let's try another one. A multiple choice quiz has 8 questions, and there are 4 possible answers to each question. Okay, let me write this down. 8 questions, 4 possible answers to each. How many permutations of the answers are possible? Okay, so the first question we have to ask ourselves is, are we saying that it's okay to repeat or not okay to repeat? Well, if you have a multiple choice test with A, B, C, and D, each question is going to have all 4 letters as an option, right? So what that means is that it's okay to repeat. Here's a picture of our test. There are 8 questions, so I'm going to make 8 boxes. Okay, here's the first question. How many choices of an answer do you have? Well, there's 4 possible answers to each question. I didn't finish writing that. So there's an A, B, C, and D. We can choose any one of the 4. That means we have 4 choices there. Second question. We still have 4 choices, right? That's how tests work. You don't have a declining number of choices. So for every question, there's going to be an A, B, C, or D that we have to wrestle with. Does that make sense? So I draw out the 8 questions, and then I figure out there's 4 choices for each question. So we have to multiply 4 times itself a whole bunch of times. It turns out to 65,000 536 ways. Holy moly. That is how, ladies and gentlemen, if two students were to get the exact same answers on a test, I mean, unless they were the right ones, it's highly probable that they might have copied, one of them has copied off the other, because there's just so many different ways to fill out a test. So that's how teachers know. 116.4. How many three-letter signs can be made from the letters in the word numeral if no repetition is permitted? Okay, so what that means is that we don't have a felt board with an infinite supply of the white plastic letters. That means we have Scrabble tiles. That's how I always think of it. If there's no repetition, well, except Scrabble has, I'm kind of mixing this up, but, because Scrabble games have more than one of each letter, but the game's put away. You don't get to look at all those. It's just one of each, okay? And we're trying to make three-letter signs. So here are the three letters. These are the choices that we have. So when we get ready to fill in the first blank, 1, 2, 3, 4, 5, 6, 7. We have 7 choices to go in. Now one of them has been used up. So when we go to the second letter, we can only choose from 6. And now 2 are used up. So what we have left is 5. Now that's all we're doing because we're only doing 3 letters in our signs. So this is the picture of our number of different ways. And so the answer is 210 ways that we could make a 3-letter sign out of the word numeral, even with no repetition. We're not going to repeat them. There's one more of these and then we'll switch to probability. Jamie has 5 places to put items in her display. She had 38 different items. Okay. 5 items to display. So let's imagine there's a shelf. Okay, there's a shelf that has 5 cubby holes, right? Like this. And it's like, I think we call them shadow boxes, but it's 3-dimensional, right? And you hang it up on the wall. And there's cubbies in it. I'm really getting into this now. Okay, and so we've got 38 items for display in this shelf that will only fit 5, right? So, how many different arrangements can we make? Well, the first question I hope you're asking yourself is is repetition allowed or is it not allowed? Well, we have to use common sense to answer that question. We've got 38 items, so if we put one on the shelf, another one's not going to magically reappear, right? We're not going to have an infinite number of items rematerializing. They're fixed. So I would say that means no repetition. Okay, we can't use the same item over and over and over. We only have one of them, all right? So when we go to fill in the first box, we have 38 choices for what to put in there. This multiplication is going to be a monster, isn't it? When we go to choose the second box, we've used up one of them, but we still have 37. Then we'll have 36 and 35 and 34. So when we multiply this together, we're going to find out there are a whole lot of ways that we can arrange these 38 items in this 5-compartment shadow box. Are you ready? 60 million ways. Holy cow. That's a lot, isn't it? All right. So this is what permutations are good for. Finding out how many ways things can be arranged. I don't think we're going to see them again this year, but next year we're going to come back to these and play with them and just complicate the scenarios. I think they're kind of fun because they're not, the math is easy. You just have to kind of logic them out in your brain. Okay, that's enough about permutations. Let's go back to probabilities. Probabilities, as you know, are statistical measures. They come from usually games of chance, like rolling a die. A die is one. A dice is more than one. Or spinning a spinner. Or flipping a coin. Or drawing a card. Right? The important thing about these events is that all outcomes are equally likely. If there's a bias toward a certain outcome, then we can't calculate the probabilities, because in order to calculate the probability, the outcomes have to be equally likely of occurring, just as they are in all of these examples that I've laid out here, right? And the basic formula, every time we do one of these things, every time we roll the die or spin the spinner, that's called the event. Let me write this way, E-V-E-N-T. Okay? And the probability of any particular kind of event, like landing on heads or rolling a 6 or drawing the ace of spades, it's equal to the number of desired outcomes, you'll remember this, over the number of total possible outcomes. All right, that's our basic formula that we will use for these problems. You've seen it before. Let me just scooch it up so you can get a good look at it. And I will let you finish copying that before I boldly dash on. Okay. Flipping. Let's do a problem, shall we? Example 116.5. Let's find out how many there are. It goes up through 8, but they're fast. Okay, 2 dice are rolled. Okay, that's like Monopoly. That's my classic 2 dice game, right? What is the probability of getting A sum of 7, or B, a sum greater than 8? All right, now what we usually like to do in these problems is it helps if we draw a picture of what's happening in these, right? If we were rolling just 1 die, I would barely think we need to draw a picture because it would look kind of like this. These are all the different outcomes. Whoops. 1, 2, 3, 4, 5, 6. I barely need to draw that, right? You know what a die looks like and the 6 different sides of it. But we're talking about 2 dice. And so that makes this a little bit more complicated. We have to visualize all the different outcomes that are possible when you roll 2 dice. And we can't just draw another one of these because there's all these wacky combinations. I mean, not wacky, but there's all these different ways they can combine. So here's what we need to draw to understand this. 1, 2, 3, 4, 5, 6. Those are all the possible outcomes if you roll the first dice. The second one can also roll a 1 through 6. So this is the second die up here, right? This is the first one, and this is the second one. And you know how that works when you're playing these games. You roll the 2 die, you throw it, you see what each of them shows, and then you add it together. So this field here is going to be all the different sums that you could possibly be able to move in the game, right? So if you roll a 1 and a 1, you get to move 2. If you roll a 1 and a 2, you get to move 3. 1 and a 3 is 4. Obviously, I'm just going to add these, right? Now let's do if you get a 2 and a 1. 2 and a 2, 2 and a 3. You see what I'm doing, right? A 3 and a 1 starts with 4. And it just goes up by 1 all the way across, doesn't it? Fill in the chart with me. I know it feels tedious, but you're going to see why it's super helpful in a minute. 5 and 1 is 6. Okay, this took us a minute to fill out, but it wasn't very hard, right? That was hardly intellectually taxing, but it was kind of, I guess you could call it tedious. Okay, so now though, it's going to be so easy to answer the questions. What is the probability of getting a sum of 7? The probability of getting a 7 is equal to the number of desired outcomes. Okay, well, the number of desired outcomes would be getting a 7. There's a way to get a 7. 2, 3, 4, 5, 6. There are 6 different combinations that will give us that 7 that we're looking for out of 36 in all, right? 6 times 6 means there's 36 different outcomes. So the probability of rolling a 7, is 1 out of 6. I just reduced that. Make sense? So as you can see, creating this chart made it a lot easier for us to answer the question. And now let's answer the other question. A sum greater than 8. Okay, well, the combinations greater than 8 would be 9s, 10s, 11s, and 12s. I'm circling it extra hard so that we won't confuse it with those. All right, so greater than 8, 9, 9, 9, 10, 10, and another 11, okay? Again, this chart makes it super easy. We can see them right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of getting greater than 8 is 10 out of 36. Remember, that's a 36. It does not look like it. And that would be 5 out of 18. So there's our answer there. Okay. The last thing that we want to talk about in this lesson is something called independent events. Let's say that we're flipping a coin. Okay, let's say that we're flipping a coin, and the first time we flip it, we want to get heads. So we would say the probability of getting heads is 1 out of 2, right? There's only 2 options, heads or tails, but we just want heads. Now let's say you flipped it a second time. What would be the probability of getting heads the second time? 1 out of 2. What would be the probability of getting heads a third time? 1 out of 2. Every single time we flip the coin, the probability of getting heads is 1 out of 2. Now, what if before we started this, we had flipped it and gotten heads 3 times in a row? Let's make it 4 times in a row. Before, okay? Does that change the probability of these 3 tosses? Does it make it more likely that we're going to get heads? Does it make it less likely? No. Previous events have no effect. Okay? So it doesn't matter what's happened in the past. That doesn't change anything. Every single time we flip the coin, we have a 1 out of 2 chance. We might get a crazy streak of heads or tails because this doesn't promise that you'll get an even number. It's just that the odds are 1 out of 2 that you'll get heads or tails, right? Now, and what it also means is that if you were to flip the coin like 500 times or 5,000 times, then you'd probably get a pretty good 50-50 split because you've done it so many times. But there might be streaks in there where you got a whole bunch of one without the other. That doesn't change the probability. It just, what does it do? It just captures certain independent events. But these throws, these flips, have nothing to do with these. So we get problems like this. A fair coin is tossed 3 times. What is the probability that it comes up heads every time? All we do is multiply them together. So the probability of getting heads 3 times in a row is 1 out of 8. Okay? It doesn't mean you're guaranteed that you'll get one. It doesn't mean anything about what will happen. It just means that's the probability of what could happen, is most likely to have happened. All right, let's do one more of these and then we'll be done. A fair coin is tossed 4 times and it comes up heads every time. Okay, this is what I was talking about. 116.8. Okay, so 1, 2, 3, 4, 5. It's already been tossed these times and it came up heads every time. And the question is, what is the probability that it will come up heads on the 5th time? None of these events matter. They're in the past, they're history. The probability of getting heads this time is unaffected, so it's 1 out of 2, just like always. Previous events do not affect the probability. Make sense? I hope so. Probability is kind of fun. Permutations are kind of fun. They're a breath of fresh air compared to some of the heavy stuff we've been doing, and I hope you had fun. All right, I will talk to you soon. Goodbye.